Uh, this video is on equilibrium of a ladder. Let us say we have a ladder AB resting against a wall, and it's resting at point B and resting here at point A on the ground, right? And this ladder is in equilibrium, meaning that it is neither going down, sliding down along the wall, neither is it sliding along the ground. So it's in equilibrium, and we're going to look at the various forces which come into play for the equilibrium of the ladder, right? Okay, before that, we need to understand the concept of forces, and particularly concurrent forces, right? The equilibrium of a ladder is a good example of concurrent forces. So let's first understand what we mean by concurrent forces, right? So let me show you this. Let us say we have an object, a wooden block may be placed on a table, right? So this is a table surface on which we have a wooden block, and say there are a number of forces acting on it, forces F1, F2, F3 and F4, and these are various magnitudes. Of course, their directions are different and there are various magnitudes. Now, what we see over here is that if I extend their line of action of all the forces, they pass through a common point, right? And such forces are known as concentric forces. So these are concurrent forces. Concurrent forces. Forces, the lines of action of whose pass a common point are concurrent forces. And if I show them in the form of vectors, let us say this force F1, right? So I take care of the direction as well as the magnitude, and if I show all the forces in sequence one after the other, and if they complete a polygon, then these forces are in equilibrium. Right? So this is the background which we require understanding concurrent forces, and then we'll shift back to equilibrium of a ladder, right? So I want to understand various forces acting on this. I know that these forces, when put together, are in equilibrium. First, let us begin by trying to understand which are the various forces which come into play. So I'll first mention the forces that come into play. One force is the weight of the ladder, quite obviously, the weight of the ladder, right? And the ladder force will act in the downward direction, right? From the center of the ladder. So this would be the direction of the weight, and this would be the line of action of the weight force. Reaction from the fall, and third, reaction from the ground. So these are the other two forces which come into play. Since this ladder is resting against this wall is going to kind of offer a reaction. Similarly, the ground is also going to offer reaction. We are going to assume that this wall is smooth, so there are no frictional forces which come into play, and hence the reaction from the wall will be perpendicular and horizontal, right? So this is the direction in which the reaction of the wall will act, right? Let us call this reaction RB. Right, so we have now the direction, line of action of force of RB. We have this new. The last one remains reaction from the ground. So this ground is going to offer reaction. Now, what will be the direction of this? Since the ladder is in equilibrium, these are concurrent forces, so they should pass through a common point. Hence, we can say that the direction of the reaction from the ground will be like this, right? Will be in this direction. So this will be the line of action of the force, right? And let us say this is the magnitude. So this is RA, right? RA. So these are the three forces which come into play. Now, as we said earlier, concurrent forces, when they are in equilibrium, if I draw them in the form of vectors, they should complete the polygon. In this case, since there are three forces, they will complete a triangle. So let me show the three forces in the form of vectors. Let us assume, let's not worry about the magnitude as of now. Let us just look at the direction. So let us say this is RB, right, the horizontal. The weight acts in the downward direction, so let us say this is the weight acting in the downward direction. So this is W, and RA, right? RA will be such that it will complete the triangle. The ladder is in equilibrium, and all these forces have to be in equilibrium. So this will be RA, right? So this is how the vector diagram looks like. Let us say this angle is theta. right? The angle that RA mixed with the ground is theta. So in that case, what will happen is this will be theta. This angle will be, if this is theta, this turns out to be theta. Okay. Now if I look at this diagram, I can conclude a few things. One is that this angle is 90 degrees, so I can conclude that RA square is equal to W square plus RB square, right? So this is equation 1 that I am getting. Secondly, if I take tan theta, right, tan theta is equal to opposite side, that means W upon adjacent sides RB. So I get tan theta is equal to W upon RB. Okay. Let's go back to this diagram. If you look at theta, right? If I look at theta, and let me call this point as D and let me call this as point. If I look at triangle ADE, right? Triangle ADE, right? Then in a triangle AED, tan theta is equal to DE upon AE, right? Is equal to DE, right? DE will be equal to BC, right? And this is AE, right? What is BC? BC is equal to Y. AE is W will act at the midpoint, so this will be half of X. So I'll get here X by 2. And therefore I can write down tan theta is equal to 2y by x, right? And therefore if I summarize this entire discussion, I have get equation 1, and equation 2 can be written as tan theta is equal to W upon RB is equal to 2y upon x. So this is now my equation 3 I can, and this is equation 1. So equation 1 and equation 3 will help me get up any unknown